Okay, before we start example one, I just wanted to go over on slide 3, it mentions that linear momentum is mv. So momentum is mass times velocity. I just wanted to mention that right at the bottom of the slide, it mentions a fast bullet and a slow train. So if I just say fast bullet here and slow train, what I mean by that, what we would normally discuss in class, is over here, let's say we've got this little bullet and it's zooming along this way, and over here we've got a slow train. It's much, much bigger. This is not the scale, obviously, but it's barely moving. It's just kind of slowly rolling along. If we look at this equation, momentum is mass times velocity. The bullet, P equals mv, has a very small mass, but it does have a very large velocity. So I kind of think of velocity as how hard is it going to be to stop something or slow it down or something like that? If you try to catch this bullet, if you put your hand in front of it, the bullet is tiny. It's like if I toss a little, I don't know, rock or something to you, or an eraser to you, right? It's not going to hurt, but a bullet, because its velocity is so fast, it's definitely going to hurt. It's going to be hard to stop this thing. So even though it's a small mass, it's hard to stop. If we think of the train, momentum is mass times velocity. Its velocity is super small. Pick a number here, 2 meters per second or 1 meter per second, or it's going very slow, but because its mass is very high, if you were to stand in front, put your hands in front of this thing and try to slow this train down, it's going to be very hard to slow down and bring to rest. So momentum can be a difficult thing. The equation is very easy, just mass times velocity, but people often ask me, but what is it? And it's difficult to kind of explain or maybe to see from this equation, mass times velocity, what is momentum? I kind of think of it as, how hard is it going to be for me to bring this thing to rest? Small mass but high speed, still hard to bring to rest. Large mass, slow speed, hard to bring to rest. If it's a speeding train and both things are high mass and high velocity, obviously that's going to be really, that's the hardest, I guess, to bring to rest. So that's just a bit of an idea as to what momentum is. And then the next little bit, I guess it's slide 4, mentions impulse. Impulse is change in momentum. And so if we think of impulse delta P, just so you know, it's also sometimes written as a J. So delta P with a vector sign or J with a vector sign is m delta V, change in velocity. Same units, but it's just the change in momentum. So again, if we're thinking about how hard is it to stop something, it's really impulse that we're talking about. And on slide 5, just at the bottom, it says discuss catching a baseball barehanded, dropping an egg on a pillow, airbags in cars, all those kinds of things. Let's imagine some eggs. Let's do the eggs. So let's say here's an egg, here's another egg. They're identical eggs, okay? Mass is equal. Let's say equal mass. This egg looks a little bigger, but let's just imagine equal mass. There's egg 1, there's egg 2, and we're going to drop them. And let's put kind of a dotted line here. For this guy, the floor is going to be right here, a concrete floor. And for this one, we're going to put, like, I don't know, a nice soft cushion here, something like this. Maybe the actual floor for him is down here a little bit. But they're both going to hit the same height. If I drop them from rest, by the time they both have fallen the same height, right here, this is going to be my velocity 1 because it's eventually going to come to rest here. This velocity 1 and this velocity 1, the speed that they're going upon impact is the same because they're dropped from the same height. This guy is going to kind of, I don't know, compress the pillow down a little bit, and the egg is eventually going to stop somewhere down here. We're going to make that V2, and that's 0. And then for this guy, its V2 is probably still right here, but I'm just going to write it here, V2 is 0. What I'm trying to show with this is that they have equal mass, equal V1. So again, same here, this V1 and this V1. The collision speed is the same. Same V2s, they're both zeros. What we know then is the impulse for egg 1, this is egg 1, this is egg 2, they have the same impulse. What we're talking about is mass times delta V and mass times delta V. Again, this is for egg 1, this is for egg 2. This delta V is V2 minus V1, and then over here, same thing, V2 minus V1. The masses of both eggs are the same. The V2s are both 0. The V1s, that impact velocity, the same. these things are the same on both sides. So what we're seeing is that their change in momentum is the same, but how they arrive at that change in momentum is 0. So on slide 5, it mentions again, change in momentum or impulse is this m delta v, but it's also this equation. Okay, so up here we said because of all these reasons, because all these things are the same, their impulses are equal. But this egg probably is not going to break because it hits a cushion. This egg is going to break. If their impulses are the same, what's different? And here's what's different. This guy, because it hits the pillow here initially, but it's brought to rest over a much greater distance, or really what's important in this case is a much greater time. Because this time is bigger, this force can actually be smaller. And for this egg, it's brought to rest very, very quickly. This time then is very small, which results in this force being much bigger. Or you could say it the other way, because the force is so big acting on it, it's brought to rest very, very quickly. So because this egg here experiences less force, it does take more time. But in this case, this less force, that means this egg can survive. This egg doesn't break, let's just say. Doesn't break. Whereas this egg over here experiences a lot more force. It stopped very quickly, less time. But again, if you're thinking about who survives, this egg breaks. Okay, and that's important. This is, again, the reason why we have airbags in cars is for this reason exactly. The airbag in your car kind of does this cushioning effect that increases the time of your head being brought to rest in the case of a collision, which means less force, which means your head's not gonna get hurt, I guess. Okay, so that's a lot of discussion. I wanted to make sure that was clear before I went on and did this example. The example here is not actually all that hard, but those concepts are kind of important. As we go through this example then, what we've got is a volleyball. So let's say here's a volleyball. It's going 15 meters per second to the right. Walter was in my class a couple years ago. Walter hits this volleyball when it's in the air, so he hits it, and then the ball's going to get sent back going this way, and V2 is 29 meters per second. And let's say that this direction is our positive direction. To the right is our positive direction. So what we know from this, we're asked to find the initial momentum of the ball. Momentum is mass times velocity. These things are vectors. I'll call it M1, and we'll put momentum 1 and velocity 1. These things are vectors. We do need to consider that. The mass of the ball, 0.32. V1 is 15. Again, to the right, that's positive. It's positive here. Momentum 1, that's approximately 4.8 kilogram meters per second. And that is to the right. This thing is a vector. Okay, so when we're finding momentum, we do have to put a direction on this thing. For the average force question, this one's a little bit, maybe a little bit trickier. We do know that impulse or change in momentum is force times time, net force, because those guys are vectors. But we also know that this impulse is m delta v. And delta v, just remember, v2 minus v1. When we sub in these velocities, we do need to consider those directions. So the mass, 0.32. V2 is 29. Remember, I chose to the right as positive, so this is going to be negative 29. That minus is part of the equation. This 15 is going in as, V1 is going in as a positive number. So this guy is negative because it's in the opposite direction. This guy is actually going in as positive. That minus sign is part of the equation. Force is what we're looking for. Time, this thing here is 1.83 milliseconds. That's what that ms is. So 1.83 times 10 to the minus 3. It's like millimeters. We're dividing by 3. We can rearrange all this and we can get some of the forces it's negative 7693 99 newtons. That is approximately, for sig digs, 7.7 times 10 to the 3 newtons. Something just to note here, so it is negative. When we get this, we're going to get a negative out of that. When we divide, it's still negative. This is negative to the right, which is our positive direction. So this answer is to the left. This guy is a vector, so we need that direction. That left makes sense, right? If the ball is coming this way, he's hitting it. He's putting a force this way to make the ball go back that way.